Okay, today still 6.2 in the first book in my notes. I present some properties about divided difference. Divided difference properties. Number two. Oh, number two is section 3, not section 2. Hermite interpolation. Hermite interpolation. Okay, take a review about what is divided difference. Yeah. Given a table about some function. About some function. Yeah, here y is f of x. There is one and only one passes through all these data points. One and only one of polynomials of degree log greater than f. Okay, yeah. There is a unique polynomial of degree log greater than n that passes all the data points. Okay. That passes all the points, all the data points, all the data points. Yeah. Only one polynomial. However, you can write this polynomial in many forms. Now let's focus on Newton's form, because Newton's form is easier to be extended to solve other problems. Say we can extend Newton's form to solve Hermite interpolation. Yeah. In Newton's form, okay, this polynomial can be written as P C0 scalar times Q0 plus C1 times Q1 C2 times Q2 and so on. Cn times Qn. What is Q? Q, the definition is Qi. This is a polynomial degree I, special polynomial. How special? Yeah. X minus x0, x minus x1, times x minus not xi, but xi minus 1. Okay. It can be proved C0 only depends on function value at x0. C1 depends on function value at x0, x1. C2 depends on function value at x0, x1, x2. Now, we don't use C0, C1, C2, Cn to denote the coefficients, but use the following notation. Yeah. F C0 depends on function value at x0. Yeah, use this notation. Now C1 use this notation depends on function value at x0, x1, and Q1. Thus C2 depends on x0, x1, x2, and Q2, and so on. Thus, thus F depends on x0, x1, x2, and so on. Xn. Then people discovered that the coefficients in Newton's form, they have other applications. They have other applications. So we give special notation and special name to the coefficients. Special notation is this, okay? Special name, divided difference. Yeah. Special name, okay, yeah. Call this, okay, call. Say xk, different name, okay. Yeah, actually, this is the coefficient in Newton's form. Call this the divided difference of order k of function f. Function f. Yeah, just like derivative. Derivative is a special limit. It's a limit, right? A limit of a quotient. Because people later find out that that special limit has many applications. So give special notation. Derivative. Special notation is this or this. Yeah. And give special name. Say similar here. Then how to compare divided difference? There is a formula. Let me present a formula today. Yeah, the formula to compute. The formula is this. I didn't have time to present the proof. Yeah, the formula. X0, x1, x2, xn. Yeah. Divided difference of order n. It can be computed by divided differences of order n minus 1. Yeah, the formula is this. Divided difference order n minus 1 from x1 to xn. Minus then from x0 to xn minus 1. Then divide by the last root xn minus the first root. Yeah. Yeah. How to prove this formula? Yeah, some people consider this formula as definition rather than, okay. Definition, two definitions. One is divided difference is coefficients of interpolation polynomial in Newton form. The second definition is this. Yeah, consider this as a definition. Okay, now this is order n minus 1. How about order 0? Yeah, order 0. Yeah. The definition is this. Function value at x0. Yeah. Order yeah. Function value at x1 and so on. Xn. Now let me prove this equation. Okay. Let me prove this equation. Prove this equation. Okay. The proof, easy. Okay. Then the proof. Then Pn. This is a degree n. Be the polynomial interpolating function f and x0, x1, xn. Yeah. That means the polynomial degree n passes all the data points. Okay. Now then Pm minus 1. Yeah, Pm minus 1. M minus 1, degree n minus 1. Be the polynomial interpolating function f and x0, x1, xn minus 1. Yeah, here. Yeah. N minus 1 here. This is a p n minus 1. What is p? Yeah. Pass all the data point is p. Okay, now further. Let q n minus 1 be the polynomial interpolating function f and x1, x2, and xn. Yeah. Let me use a different color. Yeah. This is a q n minus 1. Q n minus 1, degree n minus 1. The polynomial passes through x1, y1, x2, y2, and xn, yn. These m points. Right. The leading coefficients of these three polynomials, okay, the leading coefficients of these polynomials are compare them to Newton's form. Leading coefficient of this is this. Yeah. x0, x1, xn. Leading coefficient of this guy is x0, x1, to xn minus 1. Yeah, because this guy interpolate x0 to xn minus 1. So, leading coefficient of qn minus 1 is this. Yeah, it's this. x1, x2, then xn. Now, these three numbers, dividing difference is a number. These three numbers is related by this equation. But why? Why? The reason is easy. Okay, easy. It's easy to verify. Yeah. This polynomial n minus 1. Yeah, this guy degree n minus 1. And x minus xn. Xn minus x0 times q n minus 1 x minus p n minus 1 x. Right. Let me, I need to keep this again. This polynomial, the degree of this polynomial is n. Yeah, degree is n because degree is m minus 1. This is a degree m minus 1 and multiply by this guy. This guy degree is 1. So this polynomial degree is n. Yeah, degree m minus 1 times degree 1 n. It's easy to verify that this polynomial interpolate function f at all the data points. That means that this polynomial passes through all the data points. How? Easy. That plug in x0 in x. Check them one by one. Yeah. Okay. Then have a check. Plug in x0 in x. Then we have qn minus 1 x0 plus x0 minus xn minus x0 times qn minus 1 x0 minus pn minus 1 x0. Let me see. What is qn minus 1? Qn minus 1. Oh, interpolate the data points from x1 to xn. So I don't know what is this, okay, actually. How about this? This is a negative 1. Yeah. So minus qn minus 1 x0. How about this? By assumption, pn minus 1 interpolate the function at these points. So this should be f x0, y0, right? Yeah, pn minus 1. Polynomial interpolate at these points. That means that at these points, the value of this polynomial match the function value. The function values. So right, now distribute the negative sign. Cancel out qn minus 1 x0. So we get. So yeah, this polynomial is value at x0. Yes, it's function value. Very similar. This polynomial at x1 is function value y1. And so on. Okay, so this polynomial interpolate function f at these points. So by the uniqueness of interpolation polynomial, this polynomial should be exactly Pn. Exactly Pn. Yeah, Pn. Exactly Pn. Only one polynomial, okay, degree n, pass through all the data points. Excellent. Okay, now compare the leading coefficients. Compare the leading coefficients of this polynomial and this polynomial. Leading coefficient of this polynomial is this. Yeah. If you write this in Newton form, the leading coefficient is this. What is the leading coefficient of the left side? Leading coefficient. This is a polynomial degree n minus 1. So leading coefficient log here. But here. Okay. It is a leading coefficient of this minus this, then over this number, xn minus 1. If you expand, okay, you will see. Yeah, exactly the right side. Any questions? Can you see? Right. Leading coefficient is not here, okay? Not here, okay? So don't consider this. Consider this, okay? Leading coefficient is the coefficient of x to n. Yeah. Okay. Leading coefficient of this is this, okay? Actually, this guy. Leading coefficient of this polynomial is this. And then multiply by, this is a degree n minus 1, multiplied by x. The coefficient xn minus x0. Yeah. To compare, this will be equal. So we have this equation. Yeah, people consider this equation one of the two definitions. Yeah, definitions. I didn't have time to present this proof in the last class. Okay, now today, topic 1, properties about dividing difference. Yeah. Properties. Topic 1. Properties about divided difference. Yeah. Right. The first one. Okay. Yeah. It turns out that the order in x0, x1, xn doesn't matter. Okay. Doesn't matter. Yeah. Right. If C0, C1, Cn is a permutation of x0, x1, xn. What it means? Permutation. Then here. Yeah. 1, 2, 3, 4, 5. Yeah. This is a set of numbers. Yeah. Permutation. One permutation is here. 3, 4, 1, 2, 5. Yeah. This is a permutation. It turns out that permute x0, x1, xn doesn't change the value of dividing difference. Yeah. Then if C0, C1, Cn is equal to value doesn't change. How to compare a divided difference? Yeah, use the formula. Yeah, here I just erase. Yeah, you use the formula to compare. First property. Second property. Okay. Property 2. Number 2. Let P n be the polynomial that interpolates function n and x0, x1, and xn. Oh, here, I assume this looks distinct. Okay, this hint, they're different. Okay, they're different. Then, how close is P with to the function n? Yeah, f of x minus Pn x. How close? Yeah, we have a formula in some previous section, but use the divided difference, it can be so. This is a f x0, x1, xn, then x. Okay. How to compute this? By the formula that I have erased. Times, yeah, times product x minus x k from 0 to n. Before, okay, we have this formula. Before, take a review. We have this formula from one field. Yeah, formula. This is a 1 over n plus 1 factorial f n plus 1 sine x times this. Okay. You remember? Yeah. There is a field. Okay. How close interpolation polynomial is to the function n? So close. Then what is the difference between these two formulas? The difference is this formula requires function f is in C n plus 1 AB. Okay. Yeah, that means that this formula requires function f has derivative up to order n plus 1. Otherwise, load this formula. Then, how about this formula? This formula is true for any function f doesn't need derivative. The function may have no derivative. Okay. Yeah, this is the difference. Property number 3. Property number 3. Number 3. Number 3. If function f is in this set, function f, this notation means first, function f is defined on the open interval a to b. And this function has derivative of order up to n. And all derivatives are continuous. C means continuous. For example, sine this function is in this set. All right, and if the roots x0, x1, xn are distinct, different points in AB, then divided difference f x0, x1 to xn is equal to what? 1 over n factorial f derivative n times on function n then evaluate at some point psi. What the point is, where the point is between x minimum and x maximum. What is x minimum? X0, x1, xn. Yeah. X minimum is the smallest of x0, x1, xn. Maximum, the largest. Yeah, maximum. But it can be true. There are some other properties in the book, but we don't need those. Okay, so I just only present this three. Now the second topic, Hermite interpolation. Yeah, Hermite. Yeah. The usual interpolation is we have function values and loops. But now in Hermite interpolation, we also have the values of derivative at x0, x1, and xn. Yeah, here. Yeah, this is a copy number 2. Hermite interpolation. Now, given we have a table. Yeah, here. Here. X. This is a function value. And derivative of function value. And so on. Derivative, second derivative, and so on. And x0, suppose we know function value at x0. And we also know function value and derivative at x0, and so on. Okay. Here, in general, the general question is take derivative k times. This k depends on x0, so k0 function value available. Suppose. Of course, in practice, most of practical problems, derivatives are not available. So Hermite interpolation is interesting in theory, not in practice. Okay, now at x1, suppose we know function value at x1 and derivative of the function at x1 below. Okay, and very general. Derivative k1 times, yeah, k1 times at x1 below, suppose. K0, k1, they may not be equal. Okay. Okay, now x2, f x2 below, yeah, x2 below, f k2, take the derivative k2 times, and then x2 below, and so on. Yeah. This is a xn, f xn, derivative at xn, and okay, kn, yeah, xn, xn. Now the question is, we want to find a polynomial. Okay, so then Find a polynomial. A P, so that this polynomial matches all the data. Okay, yeah, that means that say xi, right, general point, right? I can be 0, can be 1, can be 2. At xi, the polynomial at xi should be equal to function value at xi. Yeah. Derivative of the polynomial at xi should be derivative of function value at xi. And so on. Take derivative ki times. Yeah. Derivative ki times at xi is function value ki times xi. What is I? I can be 0, can be 1, can be n. Okay. Yeah. I want to find such a polynomial that match the given data. Okay. Right. All right, let me see. How many conditions we have? How many conditions we have? Let me count. So, okay. For I, how many conditions we have? One condition, one equation, two equation. Ki plus 1. Let me see. Ki plus 1. Oh, here. No. The book. Here. Let me make a change, okay? Because ki plus 1 here. Minus 1, okay? Minus 1. Yeah. Minus 1. Because we don't, ki plus 1, we don't, the 1 appears. Okay. Yeah, here. I minus 1. Yeah. Minus 1. Then, how many equations? Ki, so many equations, rather than ki plus 1 equations. Okay, now how many conditions? Okay, number of conditions is equal to ki. Ki equations. Okay, I changes from 0 to n. So in total, how many conditions in total? In total, right, number of conditions is K0 plus K1 plus Kn, right? In total, there are so many equations. Right, now I want a polynomial with degree as least as possible, as small as possible. Then what the degree of P should be? Yeah, P, say P, polynomial. So C0 plus C1 x plus C2 x plus say Cn m xn. Yeah. I want to find a polynomial that satisfies all these conditions. Then what is the smallest m? Do you have idea? In total, we have so many conditions, so many equations. In this polynomial, how many coefficients? n plus 1 coefficients, right? Coefficients. To determine m plus 1 coefficients, we need m plus 1 equations. You agree? Now we have so many equations. Yeah. So many equations. So set K0, K1 plus Kn. Kn is equal to m plus 1. You agree? Yeah. That means that move number 1 to left side. So m is this. Minus 1. Yeah. So we look for a polynomial of degree. What degree? This degree. So that the polynomial satisfies all the conditions. This polynomial should be one and only one, unique. Yeah, let me show you two examples. Show you two examples. Two examples. Here. Let me erase. Okay, erase. Okay. Now, example 1. I will use a different color. Yeah. Example 1. Given data. Given. Yeah. This data has only one loop. Only one loop. Yeah. Given. First value at x0, we are given. Derivative at x0 we know. Second derivative at x0 we know. And here. Derivative k times at x0 we know. Now the question is, what is P polynomial of degree as small as possible? So that what is P? Such that P at x0 is f x0. Derivative is this. And take derivative k times is this. The solution is this polynomial. Yeah. P is polynomial. How many conditions? K plus 1 conditions. Yeah, K plus 1 conditions. K plus 1 equations can determine polynomial of degree K. Polynomial of degree K has K plus 1 coefficients. Yeah. Okay. It turns out that it's polynomial. Yeah, this polynomial familiar to us. Plus plus f k x0 k factorial x minus x0 k. Do you recognize this polynomial? Taylor expansion. We call this polynomial Taylor polynomial. Yeah. Have a check. Okay. Plug in x0. Yes. except the first term, all the other terms 0, plug x 0. Yeah. Okay. This equation satisfied. Take derivative on this polynomial, then plug in x 0. This equation is true. And so on. True. Interpolation polynomial is one and only one, only this one. Second example. Yeah, second example. I don't have time. Okay, I don't have time. Okay. Today Friday. Then see you Monday. See you Monday. Yeah, see you Monday.